just take a second to set up, but if you think of vector spaces and what they are, so most people are familiar with dense vectors, right? You get it from an embedding model, 1024 dimensions, some number of dimensions, floats, and they map semantic meaning so that if I have an apple somewhere in the embedded within that vector space, and I have an orange, they're closer to each other than a bowling ball. And so that, like, I think we generally get that notion. One example that I give and like when I'm teaching is imagine that you have a vector space of images mapped, and you've got one of, say, Darth Vader in one place, and you've got one of a puppy in another. And so if you go, and assuming these are images, if you go to the region of vector space where Darth Vader is and look for some other close nearby things, you're going to get various pictures of Darth Vader and Star Wars related things. If you go to the puppy, you're going to see different types of cute puppies. But the question is, because we know that the vector space maps the meaning and relationship, what happens if you go to the midpoint, if you sort of pull together or average those vectors together, the midpoint between puppy and Darth Vader? Like, what do you find in that space? And there's a lot of parameters about how the embeddings were trained and what have you, but generally speaking, it's a semantic space. What you should find when you average things together is that midpoint. Is if there is an image of a puppy Darth Vader, you're going to find it right there. And intuitively, like, we've known this for ages, since back from Word to Vec, when we talked about king minus man plus woman equals queen. Like, it's these vector operations that allow you to do math on the vectors, but to also sort of play around with meaning and sort of pushing meaning in one direction or another. So that's basic embeddings on the dense side. However, we also have sparse vectors, sparse vector spaces as well. And so if you sort of put that aside for a second and you think of an inverted index, I'm taking all of my documents and I'm breaking them up into keywords and I'm indexing those. Well, you could think of that as a vector space where there's, instead of 1024 dimensions, you've got, let's say you got 1,000,000 terms in your index. Well, there's 1,000,000 dimensions. And if a word exists in a document, then there's a 1 in that dimension. And if it doesn't, there's a 0. It's a one-hot encoding. But basically, the word banana is represented by a vector with, 1,000,000 minus 1 zeros and 1 1 when the word banana exists, right, in a document. If a document has banana bread, then banana and bread both have a 1 and everything else is zeros. So it's a sparse vector, but still you can do an AND query by putting a 1 in the two positions for the words that are being ANDed together, etc. And so if we think of sparse vector spaces and dense vector spaces as both being the same thing, the only difference is how many dimensions you have. Well, if you go back to traditional search, like in an inverted index, we do something called stemming typically. What is stemming? Stemming is taking the word like engineers and reducing it down to engineer. And if you go through the index, you might, if you stem all the words, you might reduce the index size by maybe like 20 or 40%, something like that. What you're doing there is dimensionality reduction. You're taking the number of dimensions you have, the number of words in this case, and you're reducing it down to a smaller number of dimensions where engineer now represents both the concept of engineer and engineers, or at least textually. And if you further reduce it down and you start combining words like software engineer and software developer, and you merge those into the same representation, now you've got even less dimensions. And so you could almost think of just continuing to reduce and reduce and reduce until you have a very densely packed vector, and vector spaces from sparse to dense just being the spectrum of lots and lots of dimensions that are very specific to less dimensions, but they're heavily packed. And so that's just framing this. So now let's talk about wormhole vectors. So when we think about search, what people typically do is one of two approaches. They either use dense embeddings and try to do a semantic search because we've reduced the number of dimensions down to semantically meanoof kind of relationships where I can search on meaning instead of just text, attributes instead of keywords. Or they do something like Boolean matching in BM25, where you're searching on specific IDs. And what we've learned is that BM25 and lexical matching is really great at finding specific identifiers, product IDs, things like that semantic misses, that dense vectors miss, and that dense vectors are really good at finding relationships and meaning. But if you try to search for a product ID using an embedding, a dense embedding, you're probably not going to find it because that wasn't modeled, in the space. So what people do instead is they do hybrid search, right? All right, well, I'm going to do a BM25 search over here. I'm going to do a dense embedding search here. And if I just kind of merge the results together in a semi-intelligent way, I'm going to overcome some of the downsides of lexical search and overcome some of the downsides of the embedding search, right? And on average, you get better results when you do both and you combine them together, especially if you're boosting ones that match in both cases. But they're still fundamentally orthogonal searches. I'm using one technique over here and one technique over here, and I'm getting different sets of results, and then I'm throwing them together and hoping that the right results were in one of those two sets. So with wormhole vectors, the idea is, well, what if we could actually leverage both of those vector spaces, and we could actually kind of traverse back and forth between them? So for example, if I run a search, I could execute it as a keyword search on my lexical index, my sparse vector space, find a set of documents, that document set, which Daniel Tunkelang, he's one of the guest lecturers in our AI-powered search course, as are you, Connor. Really excited to have you. But he talks about this notion of a bag of documents approach. And so the idea is when you run a query, the query is a piece of text, but what you're ultimately doing is matching a set of documents. And that set of documents collectively represents the meaning of what you searched for. So if I run a lexical search and let's say it's the word apple, right? I'm going to get a set of documents. It might have a couple of different meanings in there, right? It might have a fruit, it might have a company, but fundamentally it's matching a set of meaning. Maybe there's a couple in there. What I can do is I can take those documents and say, hey, what if I were to take those and jump over to the dense vector space? For example, we talked about averaging vectors together, pooling them together for the puppy and Darth Vader example. What if I were to average together all of the vectors that match my query for Apple, for anything, for tablet or iPad or what have you, and then take that, and now I've got an embedding that is a dense vector. What if I took that and went and ran it over in my dense vector space? And then I'm going to find the point in the dense vector space that corresponds to the underlying meaning of the documents that were matched on my lexical side. And then on the dense side, now I didn't just go hit an embedding model and say, I hope the LLM understands my domain and gives me an embedding. What I've done is I've traversed from the sparse vector, the lexical side, over to the dense side. And that's very powerful because now you can actually, if you think back to agentic search and this notion of having a loop, I could actually, as part of my query, say, I'm going to go query on the lexical side, get a set of documents, use that I call that the wormhole, right? To traverse from there, to hop over to the dense embedding space. And now I'm going to see what's nearby there that matches that lexical meaning, but on the dense side. You could go the other way as well. This is actually a little bit more interesting because it's not as intuitive, but you could go to the dense vector side. You could run a search on an embedding, find the top 100 most relevant documents, use that document set, and then actually use your lexical index to generate a textual query with keywords and attributes, leveraging something like a semantic knowledge graph. And you can generate a text query that is a structured or semi-structured query to then go run on your lexical side. So it's very similar to like a decoder. Like if you had an embedding and you pass it to a decoder and you sort of spit text out on the other end that roughly maps to what was queried. It's very similar to that, but you can actually just use your underlying index to, again, it's back to this like analytics on your index notion of like, let me find what's similar about all these documents and turn those into a textual query. And so that's kind of the general notion of wormhole vectors is think of a query not as an embedding or as a piece of a keyword. Think of a query as a representation of a document set that has an underlying shared meaning, and then use that to be able to kind of jump back and forth between embedding spaces, vector spaces. The last thing I'll throw in here is, in addition to lexical search and sort of semantic kind of dense vector search, there's also this notion of behavioral vector spaces. And so we don't think about this as much, but when you do collaborative filtering, you're taking user interactions with items and you're doing matrix factorization to try to find a set of user preferences and item sort of attributes. And those are all latent features, which is uh, they're features in an embedding space. So you can generate user behavioral embeddings that represent users. You can also generate user behavioral embeddings that represent documents. And you can actually, using wormhole vectors, not think of it as just traversing between meaning and lexical and semantic dense vector space, but also you could jump to a behavioral embedding space as well and try to find user personalization based on these things. So that's the general idea. It's much easier to explain visually. So like in the course, and I've given some talks on it. Doing it in words is harder to grasp, but that's the general idea behind it.